as we move along. Um, hey everybody, my talk is going to be about building better chatbots. So I'll go into an intro about how you can use generative AI technologies like language models as well as vector databases to build chatbots, and I'll set the ground with that. And then I'll talk about how we can improve these, right? How we can make them more realistic, so that you can actually use them for real world applications. So I'll talk a little bit about advanced RAG techniques, and I'll introduce 4 or 5 different techniques and how you can actually implement them in practice. Okay. So before we go forward, let me start off by introducing myself. My name is Zain. I'm based in Toronto, Canada. And my background, I actually studied as an engineer, and then I got into the machine learning and data science field in graduate school. Um, Prior to working at Weaviate. Weaviate is an open source vector database, so I'll talk about that in a second. Prior to working at Weaviate, I was working as a data scientist. I'm really excited about and passionate about AI and the good that it can do for us. And no, I don't think it's not gonna. I don't think that it's gonna kill us all. Right? So I think we just have to make that before I go any further. All right. So let's dive in. So I want to talk about better chatbots, and realistically, any company that's trying to build chatbots wants them to be more human, right? So I want to go through this entire conversation, um, kind of talking about what the ideal use case is. And for this application, because my background is in biomedical engineering and in digital healthcare, I chose a human doctor as our ideal chatbot that we want to mimic. Right? So if you think about the average human doctor, they study for here in Canada for approximately 7+ years after undergrad, and I think this is true for the U.S. as well. For Europe, it might be a little different, but in North America, 7+ years of study after undergrad. So that's a 4-year degree. After that, you have 7+ years of study, and in their entire lifetime of practice, they see about 100,000 patients. Okay? And so when you go to your doctor, they're basically using their knowledge of 11+ years of studying at university, plus however many patients they've seen in their entire lifetime. And they're using those resources, that knowledge, to answer and kind of diagnose the issues that you're having. Right? If we want to build a chatbot that can mimic or help a lot of what a human doctor has to do, it has to be able to do a few things. It has to have access to data, because a human doctor is able to access and retrieve and reason over information from not just medical school, but also daily interactions with patients over their entire career. Right? So this chatbot has to have access to data as well. It needs to be able to search and identify what's relevant information and what's not relevant. So a doctor doesn't really have to think about every single thing that they've studied. You tell them the problem, and then they are able to identify and retrieve the small snippet of information that's relevant to diagnose your case. Right? So the AI chatbot has to be able to do a similar type of search and retrieval type of task. It has to be able to source material. Right? If it gives you some sort of diagnosis, or it tells you some output, it prescribes some medication, it has to be able to tell you why it's doing it. So it has to be explainable to a degree. And this is what it takes to be a usable chatbot in production. So we need it to cite sources. It also, in order to do all of the above, it needs to do medical reasoning over concepts that it's retrieved. Right? So if it sees that there's a patient 10 years ago who had a similar issue, and their issue was resolved by prescribing so-and-so medication, then it has to be able to reason over that and say, okay, maybe that case is relevant in this application as well. And last but not least, it has to do all of this in real time. So it's not like the patient will come in and tell you information, and then they'll leave and they'll come in 24 hours later. And so this medical chatbot has a lot of time to do all of this stuff. It needs to do it in real time, right? So all of this is very time sensitive. So if we talk about overall what this is what a chatbot agent really needs to do. Right? And if we're comparing this to a human doctor, the bar is set really, really high. Okay? So this talk is going to be about how we can build a medical doctor, a AI-powered healthcare chatbot that can help patients. And through explaining all of the different techniques that it needs to use and the different technologies that it needs to use, you'll get a better understanding of how to build these things and actually in production, what are some reliability issues that you might run into and how to resolve some of those. Okay, so the very first thing, if we're talking about medical agents, medical chatbots, one of the most important things that it needs is memory. Right? So the most critical component of what a doctor performs is if they perform recall, they perform retrieval over a large source of memory. They have their own experience, they have their learnings from medical school. Our agent needs to access some sort of medical repository of knowledge as well. So in order to satisfy this memory criteria, we're going to use a vector database. So I usually start off my talks and I ask people how many people know about vector databases. And I've been working on vector databases for about a year and a half now, and more people are understanding what vector databases are about. And so I usually take this poll and I get people to tell me whether they know about vector databases. And so currently it's trending at around 15-20%. When I started off, I used to get people, maybe 1 or 2% of the audience knew what vector databases were. But vector databases are actually quite easy to understand, right? So let me spend 5 minutes just explaining what a vector database is. So let's dive in. So usually I like to start talking about vector databases from the perspective of normal databases. Right? So a normal database, its main job is to catalog, store information, and when you need information, it allows you to retrieve information that's relevant for your particular task. Right? So think about a SQL database where if you write a SQL filter, it'll filter and give you only the relevant things, and then you can use those to satisfy your data analysis task or whatever. A vector database is quite similar, except this retrieval that we talked about here, this retrieval action happens based on this idea of similarity. And so when you ask for something that's relevant, it'll look and see if it's similar or not, and then it'll give you all of the relevant things back. And so this is still a bit fuzzy. The idea of similarity is not one that's easy to understand. Right? So I'm going to give you another example of how this works. So imagine you've got a database, and this is a very small database just for understanding purposes. You've only got two things in your database, right? You've got an article about how to build a REST API, and you've got another article about programming languages for data scientists. Okay? And so traditional keyword search, imagine you've got these two articles in your normal keyword search database, and a user comes in and they search for the word Python here in the search bar. Okay? So now what this database is going to do is it's going to look for a string that says Python, Python, anywhere in your database. But because you don't have the word Python anywhere in your two articles, you're not going to get anything back. Even though there's a match of meaning, there is no exact keyword match, and so the database comes back and says there's nothing relevant for you in the database. Right? And if you dig deeper, fundamentally, the problem here is that the database doesn't know what you mean by the query, the keyword Python here, and it doesn't actually understand what it's storing inside of it. Okay? So it might as well think that you're searching for a Python poisonous snake. Right? It doesn't know that you're searching for the programming language. Right? So what a vector database does is it actually goes in and it searches based on the meaning of the query. So here, it understands what you mean by the search query, and then it matches and it says, okay, when you're searching for Python, you probably don't mean the poisonous snake, but what you do mean is the programming language that is used for machine learning and data science applications. And so the database understands the query, and it also understands the objects that you've stored inside of it, so it can do this kind of semantic matching of this is what the query means, and most likely this article is most relevant for this query. And so what a query looks like for a regular kind of traditional SQL relational database is like this. So you write out your query, and let's say you're interested in European cities. So you kind of have to handle all sorts of variations and flavors in which you can type this out, right? So you have to say that you might be interested in a major European city, so you kind of wrap that in some sort of regular expression, and you look for this string. But important European city is just another variation of the same concept here. right? Prominent European city, leading European city. All of these, in fact, are just they mean the same thing, but they're just different ways to write that same meaning. And in a relational database, in a SQL filter, you kind of have to search for all of these different strings, and any one of these could give you a relevant result. In a vector database, to do the exact same query, it looks kind of like this, right? Where this is a GraphQL query, but really what I'm interested in here is that I'm searching for a concept that is as close as possible to a major European city. And it's going to take this concept, the concept of a major European city, and it's going to give you back anything that's remotely relevant to this. Right? It might give you the keyword back Paris. It might give you an article about Paris and some of the tourist attractions there. It might not even have anything. It might not have the exact keywords major European city, but it's going to have a meaning match or a semantic match over the concepts that you're interested in. Right? And so this is how you can search a vector database. The next question that usually arises when I tell people this is, how does this actually happen? Right? So how can a vector database understand what you mean by the question and understand the objects that you're storing inside of it? It almost seems like magic. So I want to explain how this actually works underneath the hood and what is actually going on when you're passing in a query to a vector database. So a vector database, imagine you've got your data over here, right? And this data can be anything. It can be emails, it can be written up Word documents, it can be videos, images. For now, let's just imagine they're text documents. Okay? You're going to take all of this data and you're going to pass it to a machine learning model, an AI model. The job of this AI model is simple. Its job is to convert your data into vectors. Okay? So you take data here that's human understandable. So you can read an email, you can look at an image, and you pass it into a machine learning model. And the machine learning model for every single data object spits out a vector. And so this vector is just this array of floating point numbers. So every single object you had here has now a vector associated with it. And what we can do with these vectors, this is why it's called a vector database, because it converts all your data into vectors. You can now take these vectors and now you can plot it out on a vector space. So this is what a vector space looks like, where every green dot you see on the right-hand side is corresponding to one object. So one email is one dot over here. One sentence is another dot. An image can be a dot as well. The really cool thing about these vectors is that they preserve meaning. So in this translation from human understandable data to machine understandable data, this AI model tries to preserve as much meaning as possible. And how this shows up in your vector space is that the word wolf and the word dog are going to be closer together. The image of the cat and the word cat are going to be closer together. The green dots are physically closer together, whereas the word cat and the word banana are very far apart because the meaning is there's less of a match between the meaning over here. So these objects are semantically located, and objects that are closer together are more similar. And so really how I like to think about this is if you think about a library, if you walk into a library, the location where books are placed depend on what the books are about. Right? If you're interested in economics, you'll find those books in a particular location in the library. If you're interested in history, the history of South America, those are going to be in a different location in the library. Right? And there's an entire classification system that tells you where to put a book depending on what it's about. Your AI model is basically doing the same thing. Your AI model is generating these vectors depending on what the input data was about that decides where in the vector space the data point is going to live, right? Whether it's going to be with the other fruits or whether it's going to be with the other animals, so on and so forth. Right? So a vector database is really like a very large library where an object, you can think of an object as a book, and the books are located depending on their subject matter, and a vector database is basically a superhuman librarian who you can go to them and you can tell them, I'm interested in a book about plumbing. And they'll ask you a few more questions, or they'll try to get a better understanding of exactly what you're interested in, what material you want. And they can go out and pick out maybe the five most relevant books for you and bring them back to you. Right? This is essentially what a vector database is doing. Okay. So this idea of numbers representing meaning is actually quite common, and we use them every day. Right? The easiest example here is one of colors. Every color that you see can be represented as a three-dimensional vector, where you capture how red it is, how green it is, and how blue it is, and you can use that to plot out a vector space of colors, right? So on the right-hand side, there's a demo. I'll send these slides out later, and you can play around with the demo as well. But here you can see that this part of vector space is the red portion, where the RGB channels have a similar have similar coordinates where the colors are red. This portion is the blue portion, right? So if you have another color and you calculate out what the RGB channels are for that color, it'll locate you in a region that has other similar colors as well. And this is all we're doing with a vector database, except now the machine learning model is projecting our data into a very high dimensional vector space. It's not just 3 dimensions of red, green, and blue, but it's usually 1,000 dimensions that all capture separate meaning. Okay. So an example usage of vector database would look something like this, right? You take all of your data, you ingest it, you index it, and now you create your vector space that you have on the right-hand side. Right? Now the user comes in and they have a query. They have a question, they have something that they're interested in, and they want to get back objects that are related to that query. So this query that I've represented here as a red dot can be a normal sentence, right? So this could be the sentence "cute fluffy kitten," and this is also why people are really excited about using vector databases as a memory for language models, because vector databases can be queried using plain language, and language models are experts at generating language, right? So it's really a perfect pair where you can have a model that speaks language and you can have a database that is queried using that language to retrieve information that can be used then again by the language model. So the user comes in with a query, and the vector database performs this proximity search of, I want to identify what are all of the green dots, the objects that I'm storing that are the closest to my red dot, right? And then you return those objects back to the user, and they can use that. Right? And this is all a vector search entails. There's a lot of engineering details behind the hood, and I'd be happy to answer if people have questions about that. But really, this is all that's happening. Okay. So in short, how can we use a vector database with our medical agent chatbot? You have your machine learning model, often called the encoder. You take all of your data. In our medical example, this is probably medical literature, publications. It can be historical patient data. So you're going to take all this information and you're going to pass it into the into the machine learning encoder, this model here. And it's going to take this data and it's going to turn it into vectors, and those vectors can be stored in a vector database like Weaviate. And then your user comes along, a patient comes along, and they tell you that they're having some issues. You take that information, that sentence or that paragraph, you pass it through the exact same pathway, you pass it through the machine learning model, it generates a vector, and Weaviate, the vector database, performs a search, and it gives you back out a list of results that are relevant for this user, right? So now the doctor who's trying to help this patient can now read over relevant pieces of information before trying to resolve the patient's issues. So this is actually what a vector database is and how it performs. So now what I want to do is use this information now that our agents have access to a vector database, they can retrieve from it. I want to show you how a language model would behave like an agent, and how it would use a vector database to retrieve and reason over the information. So we're going to be building a medical agent, and our agent has to store and retrieve from a vast knowledge base. So this is going to be from our vector database. It has to search and retrieve over all this data. It has to reason over the relevant pieces of information that might be important for any particular patient that's walked into their clinic. And then it has to explain itself as well. It has to propose a diagnosis. It has to prescribe a medication, and then it has to explain why it did this. And the whole point here is that we're building an agent to assist the medical doctor in their day-to-day practice. And again, one more kind of recap, it has to do this in real time. The doctor has to be able to type in relevant information for the patient, and the chatbot has to come back within 10 seconds or 15 seconds and tell you exactly what piece of information is relevant and how it uses that information to propose some sort of diagnosis for that patient. So the simplest approach that you could take here really is the patient comes into the doctor's clinic. The doctor says, here's the information for this patient. You give it to a language model, maybe a product like ChatGPT, and ChatGPT says, here's the information that you might want to review or read over before you help this patient out. This is how you or I would use ChatGPT. We would just go to their website and we would type things in, and it would give us some sort of answer. And so here, this is the simplest workflow. If this language model is fine-tuned for medical data, because this is a very domain-specific use case. If the language model is a medical language model, it's been trained over medical literature, or it's been trained with particular patient information, it'll do much better. And if the doctor knows about prompt engineering, if the doctor knows exactly how and the right way to ask questions of this language model, you'll get better results. Right? And so for this approach, I've linked a resource here for people that are interested. This is actually a paper that talks about the right way to prompt a medical language model. Right? And they talk about the difference in performance that you would get if you were to prompt it just typically, you talk to it how you would talk to a human, versus if you were to talk to it using all the different prompt engineering techniques that make it give better answers. Right? So this is the simplest approach that you can take. It doesn't work too well, and also it's prone to hallucination. So the language model can make up a lot of information, and you don't really know what's actually fact and what's fiction. And so the doctor would have to do a lot of validation of the information that's given. Right? It also won't be able to cite sources because there are no sources. Right? The language model doesn't really have access to any external knowledge base. So it's just whatever it has in its brain, it'll pull out whatever it thinks is relevant, and you don't really know why it pulled out some piece of information here. So this is the simplest approach. It's okay, but it's not. We can't really use it in production. No doctor would ever use this because they don't know. It's unsafe actually to do this. Right? So now let's move on to a little bit to a use case that's slightly more complicated. I call this approach the RAG doctor approach because it uses the retrieval-augmented generation framework to build a similar type of answer. Right? So what this does is you go in, and I'll walk through this use case one by one. Right? Imagine you've got an entire knowledge base of medical practice information. So these can be medical textbooks, these can be medical literature, publications. This can also be medical information for previous patients. Right? So this can be a patient overview where a patient goes to the clinic, they've got XYZ symptoms, they were prescribed ABC medications, and the outcome was that their problems was fixed. Right, so that you can have lots and lots of these patient scenarios that can be stored into a vector database. Right? And so a patient comes into the clinic, and instead of just taking their information and giving it to a language model, first you go in here and you turn their information into a query, and you go to a vector database, and the vector database goes in and says, here are the relevant pieces of information in my knowledge base that are relevant for this patient, and it comes out with a suggested list of medical literature that might help in diagnosing this patient. Okay? So first, you've got this now external knowledge base that you can retrieve from. Okay? And now you use this external knowledge base to extract out relevant information, and you give that to a language model in addition to the particular information about this patient. Okay? So now the language model performs this retrieve then read because it's performing a retrieval step from this vector database. So it's retrieving relevant information, and then it's reading it and then generating the answers. The good thing about this is that now it can give you an explanation of this is the source that I read before I generated an answer. So it has an explainability component to it. And this is very important, especially for the medical domain where a good answer is not enough. You need an explanation of why the good answer was given. So in medicine, giving the right answer is not enough. Giving the right answer for the right reasons is what's required. Right? If a doctor prescribes to you the right medication, they also need to tell you why they prescribed it to you. And so this is really expected in the field. So this is the typical kind of RAG approach. Okay? I'm going to go walk through this one by one. And an interesting thing that I built into this talk is that Each part of this stack that I'm talking about here, the data set, the vector database, the language model, everything that I'm talking about is open source. I'll link the sources at the bottom. If you wanted, you can look at all this data. The data is even open source, which is quite rare in the medical domain. But this entire stack you can build yourself because everything that you need to build it is actually open source. Okay. All right. So let's go one by one. The first thing that I want to talk about is the actual data. In order to build a better chatbot, so I'm only talking about the medical domain, but you can expand it to any domain that you're interested in building chatbots around. In order to build a good chatbot, you need a rich data set. This data set might not necessarily be found in the language model training data, so you need an external knowledge base that you can enrich the context of the language model with. So the data set that I used to build this particular chatbot was the PMC patients data set. And there's a link there. If you click it, it'll take you to the source. It's open source. This is a very, very rich data set. It has about 170,000 patient summaries. Right? So imagine I went to the doctor, I had an issue, the doctor prescribed medication, prescribed some tests, and then I was fixed. That would constitute one patient summary. This data set has 170,000 of similar patient summaries like that. And they're extracted from medical literature for patients that were part of medical studies. You've got 170,000 of those articles that you can retrieve from. And it also has 1.4 million medical literature articles and their abstracts that have been extracted and they're ready for you to use and retrieve from. Okay. And because this is part of a retrieval benchmark, they actually already embed all of this into vectors and you can use this with a vector database. Okay. So this is just a screenshot from the paper, and they talk about all of the different data that you can get in this data set. So you've got papers. So you've got 1.4 million papers from PubMed, and then you've also got so this says 155,000, but the data set was actually upgraded. So if you go to that link, you'll actually see 167,000 patient information, and this is what one example looks like. Okay. So we're going to take this data set and we're going to index it and put it into a database. Okay. So the immediate next step is we know what this piece of the puzzle is. We now need to go in and put this into the vector database. Okay. So for this use case, for this application, we need to scale up the use of search, and this is what the vector database is useful for. Right? Imagine you had a library filled of 170,000 patient cases, 1.4 million medical literature articles. You need to be able to scale this up. Right? And what I mean is when a patient walks into the clinic, you have to be able to identify what are the 5 most relevant pieces of information in this library of millions of documents that are the most relevant for that patient. And in order to do this in real time, in under half a second, that's what a vector database excels at, right? You can have billions of articles, let alone forget millions. You can scale all the way up to billions of articles, and you can still have retrieval that happens within milliseconds. And so, when a patient comes to you with their information, you can now identify which are the top five or top 10 articles that are the most relevant to this patient, and you can ignore all the other articles. So for this use case, I use Weaviate, which is a completely open source vector database. The product that we offer that's managed is exactly the same as what you can build yourself if you go to that repository. So this was a great use case. And then this is how you would use it in this particular application. I talked about how vector databases work generally. I'm just going to talk about how you would use it for this particular application. So imagine a patient comes to you and they tell you that their left shoulder hurts and they have numbness in their thumb and index finger. Right? This could be potentially a really big problem. You're going to take that query and you're going to turn it into you're going to pass it through the machine learning model, and it's going to go into your vector space and outcome relevant information that are from this database. Okay? So maybe you retrieve patient cases that are relevant, other patients that have had similar injuries or similar problems, and you retrieve their information and you identify what might be relevant to read before we try to diagnose this patient. It can also retrieve articles here, right? And this is a special use case where in Weaviate, we can actually index 2 different types of knowledge bases, patient cases as well as articles, and then you can perform retrieval separately on the patient case knowledge base as well as the articles knowledge base, and then it'll give you uh, the most similar things from both of them back in parallel. Right? So here I've just to show you how that would work. I've talked about what the input and the outputs would look like. Right? And so across your millions of pieces of information, you've now got back the three most relevant patient cases, as well as the three most relevant medical literature studies that might help you resolve this patient's issue. Okay. So what I want to do is talk about how this information gets encoded, right? So in this use case, I kind of skipped over the issue of how you take all this information and you pass it into a vector database. In order to do that, in order to get all these little dots here, you have to know um, how to encode your data. Right? Given a patient scenario, you have to turn it into a vector. How I resolved this issue was I used a embedding model or a machine learning model that is specifically trained on medical data. And this is also open source. You can get access to the code as well as the paper here. This is a model called MedCPT. And this model takes patient information and it turns it into vectors. So here, the embeddings have been trained on the medical domain, so they're more able to differentiate between medical use cases. They'll know the difference between different medications. They'll know the difference between different different types of diagnoses. Okay? And if you want to use specialized embedding models, you'll notice that you'll get a higher recall within that domain. If you use a medical embedding model for a medical chatbot, you'll find that it retrieves things better because it can understand that domain better. Right? It would be like asking a specialist doctor about some medical diagnosis versus a medical student. Right? The specialist doctor might be able to give you more relevant information because it's been trained and it's studied. They've studied this domain a lot more than a medical student or even a university student. Right? And so I used a couple of machine learning models for this purpose. Right? I had a MedCPT query encoder. The query encoder is a specialist at taking short snippets of information, something that a patient might tell you about their current kind of symptoms, and it encodes that and it turns that into vectors. Right? So when a patient comes to you, you can use this type of encoder to take all the information about them and turn that into a vector. That's why it's called a query encoder, because it turns the patient's information and it turns it into vectors. It takes a query and it turns it into vectors. And I also have an article encoder. So you can take very, very large documents, abstracts, entire medical literature documents. You can have an entire paper, and you can encode that entire paper. So this would be some sort of paper, and you can encode that and you can turn it into vectors. And it's going to project the query and the articles into the same vector space. And so both of these models, one that specializes in very large articles and one that specializes in small, very information dense snippets, can be used to encode all of your data into vectors. And anytime a patient comes to you with information, you use the query encoder, you take their information, you turn it into a vector, and the vector database can now perform vector search based on similarity for you. The next thing that I did here is I actually used a language model that's trained specifically on medical literature. So this is it's called the Meditron 70 billion. It's been fine-tuned on medical literature. They took a Llama 70 billion model and they took a Llama 270 billion and they fine-tuned it on medical data. Okay? So they actually continued the pre-training, this kind of next word prediction on about 50 billion medical tokens. So they took medical papers and they just got it to predict the next word for about 50 billion tokens. And they also supervised fine-tuned it. So they gave it medical questions. Like a patient comes to you, they have XYZ problems. What are some medications you can give to them? Right? And they knew what the right answer was and they taught it what the right answer should be. So this is now a specialist medical language model. And then they validated that its performance went up. So if you take the base model that it was fine-tuned on, the Llama 270 billion, the Meditron 70 billion performs better than the Llama 2 on medical reasoning, and it also outperforms GPT 3.5, which is quite good because GPT 3.5 is a model of 170 billion odd parameters, and this is only it's less than half, and it outperforms it. It doesn't outperform GPT-4, but GPT-4 is a whole other beast. This is a really good open source language model, and because I was sticking to the kind of theme of open source, I wanted to propose an open source language model that people could use here as well. Right. So this is some of the kind of the training that this model went through. So There was some pre-training where you were doing next word prediction on the PubMed articles, and then there's also supervised fine-tuning where you took specific questions, like patient has pain in their left shoulder. What are some potential next steps or potential next tests that you can run for them? And then it had the answer, and it was trained on this type of medical reasoning tasks. Okay. So this lays the foundation of our very basic model. Right? Now, what I want to do is talk about how we can go above this. How do we use more advanced techniques to improve what this language model can do? So the very first thing you can do is to rewrite the queries. And so the main idea here is that you need to admit that we as humans don't really know how best to talk to language models. Right? Initially, we tried to talk to them like they're humans, and then we found out, well, if you have a very programmatic way to prompt them, they can actually give you much better answers. If you ask them to think step by step, do chain of thought prompting, they give you answers that are much more relevant, right? And so you can't just talk to language models like humans. You need to talk to them in the strategic way. The other thing that we have to admit is that we don't really know the best way to query a vector database, right? We might just take the information and query it, but you might rewrite the information and get much better results, right? So here, the first step is to rewrite your queries to the language model as well as to the vector database here. And there's open source frameworks that do both of this, and I've linked both of them down here. You can have a look at both of these. But frameworks like DSPY do automatic prompt engineering, automatic prompt writing, and iterative prompt improvements for you. So you can just tell it, this is the input, this is the output. I want you to tell me what the best way to prompt a language model to get me the right output is most often. You can also get a language model to rewrite your queries as well. So typically when you use a vector database, you use it in this manner, right? You take your input, you have some sort of search vector database, and it gives you the documents that are relevant, and then you give that to a language model to read and answer some output. In this case, what we're doing is we're taking a query like this, like my left shoulder hurts and I have numbness in my thumb and index finger. We're giving that to a rewriter. And the job of this language model rewriter is to restate the query in a way that's more optimal for a vector database. So this language model rewrites the query, and it says this query should instead be pain left shoulder. That's one sentence. Numbness thumb. That's the second sentence, and the third sentence is numbness index finger. Now, this is much less appealing to a human. I wouldn't just walk into a clinic and say these three things. But if I'm querying a vector database, this is maybe the right way to query that vector database. Right? So now you take your rewritten query, and the whole point is this language model has been optimized to rewrite your human-stated queries into these more machine-like queries. And then you take that query and you go to your vector database, and you get back documents that are that are much more relevant now than you did over here in this workflow. So this rewrite before retrieving and generating is a step that you can use to make your chatbot do even better. And a lot of people are using this technique in production to improve their retrieval step as well. DSPY is another framework where you can give it the input and the output. So you can give it context queries and the question, and you can give it the answers. So you can give it some sort of training set, and it will iteratively go back and say, okay, the first prompt or information that I gave it, the first try failed. I'm going to go back and I'm going to try with a new prompt and see if it succeeds. And it keeps on iterating over and over until it has the most success, and then it can give you what the best prompt is. So it does this prompt optimization for you. Okay, so that's the first step. The second step that we can do to improve this chatbot is called hybrid search. The main idea behind hybrid search is in medicine, there's a lot of keywords, right? Medication has very specific names. Different diseases have very specific names. Different anatomy has a very specific name. So the machine learning model that you're using to do semantic search might not really know about all these keywords. And so the idea here is vector search is only based on semantic similarity. And if the model doesn't know the difference between two medications that are very similar but slightly different, then it won't be able to differentiate between those. But their names might be different, and you can always differentiate between their names, right? So the idea here is we also want to take advantage of the difference between the keywords in medication, right? and this is very specific to the medical domain where keywords are very important, right? This is why you can't just start reading medical literature because you won't understand half of it, because all of the keywords, that's what doctors are trained for, right? And so when we build medical chatbots, or when you build any domain specific chatbots, you want them to use the keywords and you want them to match on keywords. And for that, we use hybrid search. What hybrid search does is it allows you to run both ways to search. It allows you to run vector search. So here, your vector database will run vector search, which will be based on similarity. So this could be based on words like hurting, pain, shoulder, and then you could have keywords like medication names, or anatomy names, or disease names, and you perform searches on your knowledge base, on your medical literature and your other patient cases based on both of these. So you perform one search and another search, and then you re-rank it. You fuse their rankings together, and you get back more relevant results. Almost all of our enterprise users that are using and building with Weaviate use hybrid search, because it allows you to tune how much vector search you want and how much keyword search you want. And so to use this, you think this is a very complicated process, but in fact, this is just a one word change. If you were doing vector search here, pure vector search, this would be a different word. This would be something like near text. If you want to do hybrid search, where you want to do both in parallel, you could just change this word to hybrid. You specify what you're interested in searching, and then it performs hybrid search for you. And so it's a very simple change to go from keyword search to now having a mix of keyword and vector search in your search pipeline. Another technique that's quite interesting is called autocut. And what this tries to do is it says, even after all of this kind of detailed analysis that you've done, this information, this kind of diligent rewriting of queries, performing keyword and vector search, you might still get irrelevant results back here, right? So maybe the patient came in with numbness in their thumb, and here somebody had a broken thumb, right? And a broken thumb and a numb thumb are quite different, but you might get back information about this patient who had a broken thumb, right? And that's not really relevant. So you might still want to prune or cut off, get rid of irrelevant results here. So what AutoCut does is it goes through and it looks in a very detailed fashion, everything that comes out of the vector database, and it matches it one for one with the patient information, and it says, is this really relevant to what the patient was asking? Right? And it tries to do the similarity analysis between the patient's information and everything that comes out of the vector database. And it says, if there's anything that's slightly irrelevant, we'll take it out. Right? And so now you can give your language model much more relevant information. So I want to talk about how you do this. So let's just take our query that we've rewritten. So now notice how this is the rewritten query, goes into your vector space. The vector database does some vector search, and you get out 6 patient cases. I've removed the example of retrieving articles. So to simplify, so in this case, let's just say we're only retrieving patient cases. So these are the 6 most relevant patient cases that have happened historically. And you also get a scoring of how similar they are to this particular patient. So this patient ID 431 has the highest similarity score. So this is probably the most similar. This patient probably had the case that's most similar to this current patient. What you notice here is that patient 1, 2, 3, 4 here, these patient IDs are quite similar because they have a high score, but then you get a big jump. Right? So patient 83 might be that patient who had a broken thumb and not a numb thumb. Right? And so what AutoCut does is it says, because you have this big discrepancy in similarities, I'm going to cut off the second group of patients that are not very similar, and I'm only going to give you back the most similar patients here. And to implement this is also a one-line change, where here you're doing pure vector search. So this is not hybrid, this is near text. And now you go in and you say, I only want to get one chunk of vectors. Okay? So the similarities are all the same here. So you get this one chunk back, and you give that to your language model to now read those 4 patients' information. And these two these 2 patient cases never reach the language model, so that it won't get misled. Okay. And all the details here, if you're interested in implementing this, they're also, I've linked the source here as well. The last thing that I'm going to talk about is re-ranking. And so what re-ranking does is it allows you to take those scores that I just showed for every single patient, and it allows you to take another machine learning model, and this model reads over the information in much more detail. And so here it's going to take the patient information and it's going to compare it one by one to every single thing that comes out here. And it says, does this really deserve the highest spot? Is this the most relevant? And it re-ranks all of the retrieved patients based on how similar they are. And so here it'll retrieve more similar cases and it re-ranks them, right? So I want to show you how this actually happens. So let's say we retrieve, here we retrieve a lot more cases because we want to re-rank them. So the same query comes in and we retrieve more patient cases here. And they all have their own similarity scores. The re-ranker says, forget these scores. I'm going to now take a much more heavier model. It's going to take slightly more time, but I'm going to compare this query to every single patient one by one. And now I'm going to re-rank them based on how similar I think they are. So maybe the most similar patient here that the vector database thought is actually not that similar, and the re-ranker model demotes it down to the third most similar. It takes a third most similar one here and it promotes it up. So it does this re-ranking and shuffling step, and now it rescores them. And these are the scores that are going to be paid attention to, and what the language model will then be given to reason over this new patient's information. And again, this is one simple change in if you're using Weaviate to implement this re-ranker module. There's open source re-ranker models as well as proprietary re-ranker models that we've integrated with that you can use this in your chatbot pipeline as well. Okay, and that's pretty much the end of it. We've covered how you can build this AI-based chatbot that can retrieve from a knowledge base that's larger than any human's knowledge base. It can provide sources of how and why it came up with a particular diagnosis, can reason over patterns of historical patient information and medical literature, and it does this in real time, right? So this entire vector database retrieval step and language model generation takes within a second. It takes longer to generate than it does to retrieve. Retrieval takes only milliseconds, but it's all in real time. You can go to the doctor can have this potential tool, and this tool can suggest things for the doctor to consider before they resolve your issues. If you guys are interested in this, have a look at some of the technology that we're building. You can scan the QR code here. If you do have questions, feel free to reach out to me. You can reach out to me on any of my platforms. I'm also on the Slack channels here, so you can reach out to me there. I'm always happy to get messages, and we can connect offline as well. Thank you, everybody, and I hope this talk was helpful for you, and you can take some of the information that I've provided here and apply it to some of the chatbots that you're building. All the resources are linked. I'll send out these slides later on to the organizers, and they'll share it with you as well. Thanks, everybody. Thank you, folks. I'm just reading your comments here. Thank you so much. If you do have any specific questions, just feel free to reach out to me. I'm always happy to set up a meeting one-on-one if you would like as well. Right. Take care, folks. Have a great day. Bye.